So
Okay.
I got that going.
Yeah, I was looking for the video on your announcements, and I couldn't find it. I was like, well, I wonder, did she record it or?
Yeah, I thought I did, but obviously I didn't because it wasn't available. So, slight panic attack there at the end, but oh well. There are other videos, so it'll
That's
it'll
all
be
right. I was looking yesterday too.
you're right. It was a rough day yesterday. So today we're
I
going through the
think for
last.
everyone, yeah.
Yeah, exactly. We're going through the last four sections, and this shouldn't be too bad um, because sections 25 and 26 basically cover the same stuff, and 27 and 28 cover the same thing. So basically, we're covering two sections. It's just spread out over four, so it'll make it a little bit nicer, a little bit easier, hopefully. So, all right, let's go ahead and just get started with this. So with these four sections, there are the four web work assignments, two Excel assignments. So the trend line assignment in Excel deals mostly with section 26, and I actually will do an Excel demonstration in this section today, so you can kind of see how that looks. And then the exponential growth indicator, that's section 27 and 28 goes together. So we got two quizzes, two discussion boards, and make an appointment for exam 3. Remember, the hard due date for all of the unit 3 is next Saturday at noon. So if you don't have your exam already scheduled, you might want to do that. All right, so jumping into sections 25 and 26, linear models and scatter plots. So the big thing with linear models is, I guess, why they're linear models. If we graph them, pretend those are straight lines. If we were going to graph something, again, pretending it's a straight line, this would be a linear model because it's a straight line. That's what linear means, right? Line. So these three, the slope and the y-intercept, we're going to talk about how those relate to this linear model, and then how would we write an equation for that model. So do you, in all of your math background from however many years ago, do you remember anything about slope and y-intercept? And it's okay if you say no.
No. No.
Okay.
Do not.
What? I turn my volume.
I do not.
Okay, so when we're talking about slope, the slope of a line talks about basically the steepness. So if you kind of think about, for this particular line, it has a common change that we can go up and over the same amount every time, and we always end up on the same line. That's the concept of slope. So it describes the steepness. And I'm on my home computer at my mom's house, so my handwriting is going to be especially bad today. But slope is the steepness of a line, and slope can be positive or negative, right? This is a positive slope because the line is going up. If we had a coordinate plane and the line going down, that would be a negative slope. So line going up, positive, line going down, negative. Now we are going to have to find the slope, and there's a little equation for that, and it is on your yellow sheet, that formula sheet that you have. And that's the formula for slope is y2 minus y1 over x2 minus x1. And if you don't really know what that means, that's fine, right? We can kind of go back to ordered pairs, right? Ordered pairs are x and y. So x always comes first in our ordered pair, y always comes second. The little letters that come behind it simply means if I have two ordered pairs, the first one might be x1, y1, and this would be x2, y2. It just shows which x's are paired with which y's in an ordered pair. So those little numbers have no meaning. They just kind of, they place them together. So x2 and y2 are married, x1 and y1 are married. So you'll notice the ordered pairs have to be right on top of each other in that slope formula. One other thing that I want to hit just right now while we're talking about ordered pairs, anytime we're talking about time, in any case, that will always be our x value. So when you're reading a problem and they talk about years, minutes, weeks, anything that deals with time, they're describing your x value. Because we will get to that point where we have to write coordinates. Okay, so that's kind of an overgeneralization of slope. We could talk for 4 hours on slope, but we'll cut it to just 3 minutes. And the next thing we're going to talk about is the y-intercept. So when we look at the graph that I drew here, which kind of looks like a dinosaur, the y-intercept, right, this is the y-axis and this is the x-axis. So the y-intercept is where my red line crosses the y-axis. So in this case, that ordered pair might be 0, 2. 0 because it didn't move left or right on the x-axis, and 2 because it went up 2 spots on the y-axis. Right? So the y-intercept is where the graph crosses the y-axis. Now, something special about the y-intercept is that the x value is always 0. And that has to be true if you want to have a y-intercept, because any point that I would put on this line, we didn't go left or right on the x-axis at all. We just go up and down. So the y-intercept can be positive or negative, but it has to have an x value of 0. So something to remember. Now, when we're talking about linear models, slope is identified by the letter M. Don't ask me why, it just is. And y-intercept is denoted by the letter B. So when we go to write our linear model, okay, I'm sure you've seen this before. Y equals mx plus b. Yes, have you seen that before?
Mm-hmm. Yes, I have.
It haunts many people for many years. So this linear model, right, you'll notice M and B represent your slope and your y-intercept. The x and y have no little numbers because that x and y in this formula represent every point along our line. So any ordered pair that we would shove in there would be on this line. And this allows us to be able to predict future things. If we can create a linear model from past data, we can use that model to predict future data. And that is a main purpose of linear models. All right, so that's all the backstory of this stuff. Now we're going to use it. We're going to do 2 different types of problems with linear models. We'll see how that goes. Okay, any questions so far?
No, actually, this is, I do remember some of this.
It's like riding a bike, right? It all comes back.
Yeah.
We'll go with that.
Kind of, sort of.
Right. All right, so let's start with this first one. I call these the easy ones because there's not a whole lot of math to do with it, which is always a little bit easier. So we've got the cost of a cell phone plan is $30 a month plus 10 cents per minute. So we're focusing on 1 month at a time. Now, when you are differentiating, right, this problem they give you, it's $30 a month plus 10 cents a minute. And you have to differentiate which one of those is the slope and which one is the y-intercept, right? So sometimes it helps to think through. I want to go back to my previous picture for just a minute. Oh, I forgot I had to erase it. Okay. Remember on my picture, when I went up, I talked about the slope was a constant change, right? So the slope is something that is a recurring change. It happens over and over and over. Whereas the y-intercept happens one time. It happens when it meets the y-axis, and that's it. So the y-intercept is one and done, and slope is recurring. So that's kind of the biggest way to differentiate when you're given problems. So we go to this problem, and we read that again and say, okay, I have $30 a month and 10 cents per minute. If I'm talking about my cell phone bill for this month, which one of those costs happens one time, and which one is a recurring cost?
$30 would be one and done, and the 10 cents would be recurring.
Exactly.
Right?
Exactly. Yep. Because if you pay $30 a month, no matter what, no matter how much you talk, you pay at least $30. So the one and done becomes the y-intercept. So we know that our b value is 30. And the 10 cents per minute, and the word per is kind of a big key, per minute. So for every minute you talk, you incur this 10-cent charge. So there's the recurring piece. So our slope is 10 cents, right? The recurring charge is the slope, y-intercept is the one and done. All right, so what would my model look like if those are my slope and y-intercept? We always start with y. You always start with
y.
y.
It would be positive, wouldn't it?
Slope is positive, yes, because we're talking about total cost. Yep.
Okay.
Yep. So y equals, we start with our slope, so 10 cents. The number after our slope comes our x value. And then the y-intercept, that is also positive because, again, we're talking about total cost of your cell phone. And unfortunately, nobody subtracts for you. You got to pay it all. So this purple equation here would be the linear model to predict our cell phone bill for however many minutes we want to talk. Okay, and that leads us into letter D, which is what do x and y represent? And I want to answer this actually by backtracking. If we go back to letter B, which is what is the y-intercept, right? We said B is 30, which is totally a true statement. As an ordered pair, it's 0.30. Because when I talk for 0 minutes, my total bill is $30, right? That makes sense to you?
Mm-hmm.
From a cell phone standpoint. And then if I would talk on it, right, I get 10 cents per minute on top of that. So when you think about what do X and Y represent, you can kind of use your Y-intercept to guide you, right? X, if you look at the X value here, represents what?
The minutes.
Number of minutes, exactly. So X represents the number of minutes, and Y represents
The bill, $30.
exactly and it'll be your total cost, right? If you don't talk at all, the total cost is 30. But if you start talking on the phone, you're going to have more bill, right? So it's not crucial if you're like I can't really figure it out. Sometimes when you're trying to do like parts E and F, it'll come to you. So let's do those next. Part E. What is the monthly cost? So we're trying to find the monthly cost, which we know is Y, if you talk for 76 minutes. And we know that minutes is X. So what am I going to do with that 76?
Would you have to plug it into the Y equals MX plus B, or
Yep.
since you already done that, you do the M equals Y2 and minus
Nope.
Y1?
No, you're right the first time. Yeah. So once you have the model, then you can use it to answer all kinds of questions. So this is saying, you know that you talk approximately 76 minutes a month. What is your bill going to be? So you can type it in. If I know that my minutes is 76, well, minutes is represented by X. So wherever the X is in my equation, that's where 76 goes. And now I can solve this equation. So my first step would be to multiply 76 times 10 cents. Then I add 30. And what's the total bill?
$37.60.
Yep. So if you talk for 76 minutes, your bill will be $37.60. So that's one application of the linear model. Part F is the other application, and that's working backwards. Let's say that you can only afford a bill of $43, right? So your monthly cost cannot be more than $43. And we know that the monthly cost is represented by Y. And I'm trying to find the number of minutes, so I need to find X. So when I look at my equation, I know, the line here, I know that my bill is 43, and I need to find this value of X. So we have to solve this new equation. So this is one that tends to confuse more people because we have to work on both sides of the equal sign. So in solving the equation for X, right, whatever is touching the X is the last thing we want to do. So we want to stay away from that 10 cents for now. We want to get rid of this 30. So how do I move 30 to the other side?
Subtract.
Exactly.
30 to both sides.
Yep, perfect. So we subtract 30 from both sides. So 43 minus 30 leaves me with 13. And then I'm still left with the 10 cents times X. So now I have multiplication on that side. What is the opposite of multiplication?
Division.
Perfect. So we're going to divide by that 10 cents to get it away from the X. So 10 cents divided by 10 cents is 1. So I'm just left with 1X. And 13 divided by 10 cents?
130.
130 minutes. So if you know you can only spend $43 a month on your cell phone bill, then you can only talk for 130 minutes. All right, so those are the two different applications of this linear model. All right. Questions, comments, concerns, suggestions on that one?
No.
Okay. So that's one way that we can deal with linears, and that's right. Again, they gave us the information. We didn't have to find it. It was given. Unfortunately, they don't always give you what you need. So we're going to look here at number 2. Population of a town in 1970 was 5,600, and in 1995 it was 4,100. So we're going to go through kind of the same dealio. So part A, here's the thing. If you want to find a linear model, you've got to have slope and the y-intercept. Those are two things you have to have. And when you're just given some data, you don't necessarily have either one. So you're going to have to either find it or create it, which, yes, I just said create dealing with math. So we're going to create two ordered pairs to start with, and we need one that has an x value of 0, because if we have an x value of 0, what does that give us?
The y.
Exactly. So if we have one where
Or
x
the
is
slope.
0, yeah, you're right. It gives
Or
us the y-intercept.
Sorry.
You're good.
Intercept, not slope.
Well, you said y, so that was good. All right, so when we look up
Okay.
here, I'm going to use colors to kind of keep them together. In 1970, the population was 5,600, so those numbers go together. And then in 1995, it was 4,100, so those go together. Now, earlier, we talked about if you have time is always x or y. Which one?
Time is the x value.
Time is going to be x. So 1970 and 1995 are years, so those are going to represent our x values. Okay. Now, and because we need an x value of 0, neither 1970 or 1995 equals 0, right? That they don't. This is where you get to be creative, and you get to say, you know what? Let's let 1970 be x equals 0. We're basically saying, obviously, we don't care about anything prior to 1970 in this problem because that's where the problem starts. So if we do that, we can say, okay, then we have an ordered pair. I guess I'll put it down here. We have an ordered pair 0, 5,600. Because 0 is 1970, and in 1970, the population was 5,600, right? Picking up what I'm throwing down?
Now, can you choose either one, or do you have to start what the most recent is?
Mathematically, you can choose either one, but generally it's easier to start with the oldest year that you have because that's your starting.
Okay.
Otherwise, you'll end up with, I mean, your slope would end up being the same. It might be a different sign, positive versus negative. The math would work out the same. It's just general practice that you always use your oldest year as 0. But okay. you should get the same answer. You'll have a different y-intercept if you use the other one. But in terms of like predicting future populations, you would get the same answer.
Okay, that makes sense.
Okay, now here comes the big question. There's one ordered pair because we let 1970 be x equals 0. So now my next year is 1995. So if 1970 is 0, what does 1995 want to be?
The 4,100.
Well, that's the y value, yes. But what's my x value for 1995? Think about how many years after 1970 is 1995?
I would take 1970 minus 1995.
Well, how many years are between those two? Yeah, you can subtract them. Yeah.
25.
25. So if 1970 is equal to x equals 0, then 1995 is equal to x equal 25 because it's 25 years later. That makes sense?
Gotcha.
Yeah, yes. And that's the thing that you kind of got to keep track of. Okay, if 1970 is 0, that means everything else is based off of 1970. So everything else is in comparison to that year. Okay, so those would be our two ordered pairs. And recall, because my x value is 0, 56 is our y-intercept, right? So 5,600 is our value of b. Just for future, because we're going to need that here in a minute. Okay, so now we're ready to move on to B, where it says find the slope. So this is where, I mean, it spells it out. This is where we want to use our y2 minus y1 over x2 minus x1. So the question is, which one of the, okay, so 5,600 and 4,100 are both y values. Which one of those is y2 and which one is y1?
4,100 would be y2 and 5,600 would be y1.
Fantastic. You could have said it the other way, and it would have also been correct. Because it really doesn't matter. The key is, if you start with 4,100 for your y's, you have to start with 25 for your x. That's all that matters, is that your ordered pairs are on top of each other. Mathematically, you'll get the exact same answer, no matter which way you do it. You just have to make sure your ordered pairs line up on top of each other. Okay. All right, so then we can subtract. So we have negative 1,500 over 25. And we can continue to reduce that, and we should get negative 60 over 1. And you can just write that as negative 60 if you would like. But I want to talk about what that means. So if you recall, that slope is the y's over the x's, right? And our y values are population. So this basically means that our population decreases by 60, and it decreases because it's negative, right? Just like with absolute and relative change, negative implies a decrease. And on the bottom, it's years since 1970. So our population decreases by 60 people for every 1 year after 1970. That's what the by definition, what the slope means in this particular problem, right? Make sense?
Mm-hmm.
Okay. Sometimes I think it's nice to actually see why it works or what it means. Okay, so if this is M and we have B up there as 5,600, what would my linear model look like?
Y equals -60 times, what was it? Is it 0?
X.
Or X.
There you go. That's all right. And then what comes after -60x?
Let's see, so it'd be 5,600.
Yep, plus 5,600. And it's positive because we have that many people. Yeah. So recall that in your formula, your model, you're always going to have an x and a y, always. And then the slope and the y-intercept are the two numbers. Okay, so that's our model that we can use to do predictions after that. So looking at letter D, we want to predict the population for 2017. Okay, well, what x value are we going to use for 2017? How do you figure that out?
From the 1970?
Yeah, exactly. Since 1970 is our starting point, how many years after 1970 is 2017?
Don't laugh, but I have to use my calculator. 47.
47. Good. I'd rather use your calculator than guess and get it wrong. All right, so 47. So that means our x value is 47. So we go back to our model and we plug 47 in for x. Right. Again, you multiply first, make sure you keep that negative in there, and then you add 5,600.
I got 2,780.
Beautiful. So assuming that our population continues to decrease by 60 people a year, in 2017 we'd have 2,780. Right, there's the big thing with linear models is that you expect or you predict the same increase or the same decrease every year or every time period, that constant change. So that's the thing. All right, that's basically section 25 in a nutshell. All right, and these problems get a whole lot easier and you get a whole lot faster the more you do. So there are quite a few in the packet, and then there are more in the back of the packet with the 080 material. There's more problems back there. So the more you do, the easier they get. And you can kind of see how they all relate. Okay, so let's go into 26. 26 kind of throws in scatter plots on top of our linear models. So a scatter plot, have we talked about scatter plots at all? I feel like they've been in here somewhere. Okay, but basically this is a scatter plot.
I think it was along with the histograms back there.
Very, very possible, right? So a scatter plot is basically a bunch of dots on a graph, and a trend line says, you know what? This line right here is the best fit for those dots. It cuts right through, because in real life, almost no data is perfectly linear, right? It's all scattered all over the place, hence scatter plot. But a trend line allows us to assign a linear model to it so that we can predict future stuff, right? So that's what so the trend line would be represented by this red line here. Now, the linear correlation coefficient is denoted by the letter R, and we will get this from Excel. I will show you that in just a moment. But the linear correlation coefficient describes how linear your data is. Okay, so if you have, in this case, again, I drew a positive line. The largest positive value of R you can have is 1, and that means it's perfectly linear. That would be all of your dots on a straight line, perfectly linear. The dots that I have here would probably be closer to maybe a 0.4 because the dots are not very close to the line. The closer the dots are to the line, the closer R is to 1. Okay, and that deals with correlation. How closely correlated are my horizontal and vertical axis? Now, if I would draw a negative line, right, then it has a negative correlation coefficient. So if it's perfectly linear, everything in a straight line, R would be -1. Okay, and again, it can be negative anything else depending on where it's at. But you cannot have an R value bigger than 1 or less than -1. It's got to be somewhere in between there. All right, so I think now is the Excel portion. Yep. Okay, so I got to get out of here. Get out of here. Okay, so in Excel, and I think you do have a trend line exercise in Excel, so this might be nice to see firsthand. So I have 2 pieces of information, weeks, right? And notice weeks is time, so there's my x-axis, and then I have dollars, which is just random. So what I'm going to do is I'm going to highlight my data, and I'm going to go to Insert. I'm going to pick these little dots because they're a scatter plot, and voila, I have created a scatter plot. Now, when I hit this plus sign over here, it allows me to add axis titles. So I can change this one down here to weeks. And over here, I put dollars, right? Because I think one of the things on your requirements is to have labels. You need to have labels on here. So then, if you look, I have a scatter plot, but I want a trend line. Okay, so I clicked back on my graph to get that plus sign to appear again. And when I click on that plus sign again, all the way at the bottom, you see trend line. So when I click that, you can see this straight line that shows up between my data. And this is why Excel is fabulous. If you wanted to create a trend line from this data, I'm not even really sure where you would start in terms of doing it by hand. But Excel does the line of best fit right away. So if I click on that line, you see this crap that showed up on the side, right? The format trend line over here. Mm-hmm. If I click on the bars, you can see that linear is lit up. And when I go out of the bottom, it says display equation on chart and displayed R squared value on chart. And then I can just click and drag so I can see it. So it automatically finds the y equals mx plus b model for you for that line, right? Slope and y-intercept. And it gives you an R squared value. All right, so there's our model. We could use that for future predictions. But what I want to talk about right now is this R squared. Because R squared is not what I want, right? They tell me that R squared is 0.2828. But R squared is the coefficient of determination. We want the correlation coefficient. We want R. So how do I go from R squared to R? How do I unsquare something?
Square root it.
Square root it, exactly.
Yeah.
So if we take, yep, that was perfect. So if we square root both sides, 0.2828, square root, I'm using my cell phone, so I don't know if this is right, but 0.5318, is that what you got?
Yeah, that's what I got. Yep.
Okay. So our linear correlation coefficient is 0.5318. That's not very high. So I would say there is a weak positive correlation between weeks and dollars, right? Because those are my 2 variables here, weeks and dollars, and it's the positive correlation because we have a positive slope. Your value of R and your slope, those signs will always be the same. All right. Okay, I want to show I want to change some values in here because I want to talk about a -1. So you can kind of see things will change as I change numbers here.
Yeah, the more I learn about Excel, the more I like it.
Right? When you know how to use it, it is fabulous. It is fabulous. Okay, so I changed my dots. You can see that these dots are a whole lot closer to the line. And when I do that, look how much my R squared value increased. Now it's 0.9602. It's a whole lot higher. You can also see that my slope is negative because my line is going down. So keeping up with what we were doing, right, R squared is 0.9602. Again, we don't want R squared, we want R. So if I square root both sides, what is the square root? I'm just going to let you do it. My phone's crap. What is the square root of 0.9602?
I got 0.9798. So I don't know how far you wanted to go.
Nope, that's perfectly fine. Yep, so there's your number. But okay, remember, since this is going down, right, we have a negative slope, we need to have throw a negative sign out there. And that's probably the most commonly missed thing for people, because your calculator spits out a positive number, and it always will spit out a positive number. You have to decide if it's positive or negative based off of the slope of your line. So because my slope is negative, my R value is going to be negative. Now, this is very close to -1. So I would say this is a strong negative correlation between dollars and weeks. Look at my hand right now. Right, and it's strong because it's really close to -1. Okay. All right, questions about Excel or the linear correlation coefficient?
No, that makes sense.
Fantastic. That's section 26.
Oh, wonderful.
Right? I love that section. Okay, let's go back to the PowerPoint and let's talk about exponentials. These will go pretty quickly as well, simply because once you do 27, 28 is the same thing, pretty much. Okay, so exponential growth. With linear growth, right? So before we did straight lines. Everything was linear. Well, now, if here's my coordinate plane, if I'm talking about exponential growth, my graph looks more like this, right? It's a curve. So exponentials are curved, linears are straight. There's your big dealio. Now, we've got a formula for this, and I believe it's also on your yellow sheet. And don't freak out when you see this, because it's super easy once you understand what all of this means. Okay, so we have A equals A naught times growth factor to the T. So this A over here is our ending amount, which makes sense because that's all by itself. This little 0 just implies the initial amount. So whatever we're starting with, if you think back to when we did compound interest, our principal, same concept. Okay, so there's our initial amount. The growth factors, we're going to get to that in a minute. And T is our time. And time is in whatever periods we want to be in, days, minutes, weeks, hours, millennia, whatever, it doesn't matter. Fine. Okay, so that's the formula we are going to use in section 27. Now in section 28, when we get to exponential decay, the GF is going to turn into a DF, and there's the only difference. So you're going to love it. Okay, so let's talk about the growth factor. Now, the easy thing is, if they give you keywords like double or triple, that makes things easy, right? Because double, growth factor is 2. Triple, growth factor is 3. Unfortunately, most things don't double or triple because that's just not how the world works. So the growth factor is generally given by 1 plus the percent increase. So if I have a 3% increase, to find the growth factor, I would take 1 plus, what is 3% as a decimal?
0.03.
So my growth factor would be 1.03. Boom. That's how you find your growth factor. Now, the reason doubling is 2 is if you think about it, if something doubles, that means it has a 100% growth, right? Because it doubled. So that would be 1 plus 1, 100% growth, which gives you the 2. So that's why it works. It really does follow this same pattern. So 1 plus percent increase gives you the growth factor, and that's what gets chucked inside the parentheses. Correct. All right. Can you still see? Oh, phew. Okay. So this is a beautiful table, and I'm not going to make you find all of these values because I'm just not that mean, but I want to talk about how it works. So
thank you.
You're welcome. In the initial piece here, we can't find the absolute relative change for the initial week because remember, absolute change is new minus old. Relative change is new minus old divided by old. And if you're in the first week, there is nothing old. So it doesn't work. Right? So, okay. So if we're working through week 1, 14 minus 10 gives us 4. If we take new divided by old, we end up with a relative change of 0.4. Continuing on, right? These are sections 23 and 24 that we did yesterday. And
I haven't gotten to sections 23 and 24 yet.
Oh, that's right. That's okay. So this is just this is a review. And this kind of ties in 23 and 24 to sections 27 and 28 because, well, and 25. It all goes together, right? You got to love math. All right, so the first question we're going to ask is, which one is the same, absolute or relative? Looking at the values that I put in, are the values for absolute change the same or are the values for relative change the same?
Relative change.
Exactly. And you might recall from yesterday, you might not recall from yesterday, that relative change is also known as percent change. Right? We talked about that yesterday. And these are all positive. So not only are they percent change, but they're percent increase. And we just talked about growth factor is 1 plus the percent increase. So the fact that relative change is the same means we have an exponential model. And we're going to get to in a little bit of what does it mean if absolute change is the same. That's the last problem of the day. Okay, so how do I find my growth factor knowing that I have an exponential model? I mean, I wrote it at the top, but with the numbers that we have, how do you find the growth factor?
1 plus the 0.4.
Exactly. So 1 plus 0.4 gives us 1.4. So there's my growth factor. And anytime you are growing, that value has to be bigger than 1. Because think about it, you're multiplying. And if you multiply by something bigger than 1, it's going to get bigger. So that's what we want. All right, so now we're ready to write a model in part D. So we'll kind of walk through this one together. So the model, our ending amount equals, what's the beginning amount? How much did I start with?
You started with $10.
Started with 10. So that comes first. We just found our growth factor, so that goes inside parentheses. And then we raise that to the t power. And those variables are, they're arbitrary. You can use any variable you want. If you prefer x and y, you can use x and y. It really doesn't matter. In WebWork, I would recommend using whatever variables they discuss. Because that will help, right? So now we have them, and I think almost writing models for exponentials, they're almost easier than linear. So part C, let me figure out what I'm talking about. Week 6, what am I going to do with that 6?
Put it in for the t.
Yep, because that's time, right? So A equals 10 times 1.04 raised to the 6th power. And depending on your calculator, it might depend on how you plug this in.
I got 75.29. 295.
295, yep. So it rounds up to 30 because we're talking about money. Yep. So in week 6, you'd have 7530 if it continues to grow at this pace, right? And there's exponentials in a nutshell. We're going to do more, but that's basically it. Okay. All right. So let's do one without a table. Frogs increase at a rate of 32% every week. This is completely made up data. If there are currently 40 frogs around my pond, how do I write a model to show this? What do you need to find first before you can write a model?
The growth factor.
Exactly. Perfect. What is your growth factor?
32% or, well, I guess 0.32.
And what are you going to do to that 0.32?
Right. Add it to 1.
Perfect. 1 plus 0.32. Yep. So your growth factor is 1.32. All right. So let's put it in a model. What is your model going to look like?
What does the A stand for? I didn't.
A is your ending amount.
Ending. Okay. So the 40.
So ending amount equals 40. And then in parentheses.
Oh, sorry. Yeah. Times 1.32.
Yep. And we raise that to the t. Anytime they ask you for a model should have 2 different variables because they have to account for both the horizontal and vertical axis. So when it says write a model, make sure you have, in this case, A and T, right? When we did linear, we used X and Y, but you should always have 2 variables for your models. Okay, now what do I do in part B when it says how many frogs will I have after 10 weeks? What do I do with that 10 weeks?
Put it in for the t in the
Exactly.
equation.
So A equals 40 times 1.32 to the 10.
$642.39.
Yep, and we're going to round to the nearest.
Or 642.
Because we're talking about frogs, and you can't have a partial frog. Even if you cut a leg off, it's still a frog, right? So,
Right.
yeah,
Yep.
exactly. So you do, losing my mind here. So in that case, 642 frogs after 10 weeks, right? Questions on that one?
Nope.
All right, so that's section 27. Let's go to exponential decay. So as I said earlier, the only thing that changes in the formula is that now you have a decay factor to the t. So if you would graph these, it goes down, right? It's a curve, starts high and it decays, so it's going away, it gets less. So if you understood section 27, we're pretty much going to have the same. Oh, do I not talk about decay factor in this one? Guess I'll do it on this page. Decay factor, 1 minus the percent decrease, which should make sense. It's going down, so you're taking it away, right? Growth factor is positive. We added the percent increase. Decay factor goes away, so we're subtracting the percent decrease. Okay. All right, so we're going to go back to a table, and again, I'm not going to make you fill those in. I will fill them in for you. I think. Okay, so we have negative 24, negative 0.2, negative 19.2, negative 0.2. Why are all these numbers negative?
Because it's a decrease, negative slope.
Exactly. Things are decreasing. Since the values for the dollars are decreasing, we're going to have a negative absolute and relative change. Okay, now what's the same, absolute or relative?
Relative.
Relative. And if relative change is the same, what does that tell you? Relative change means we have
0.2 or 2% decrease, or 20%.
20%.
You move it over.
Yeah.
20%. Yeah. Sorry.
You're good. So 20% decrease, and that means we have an exponential function. Right? It's exponential because of the percent decrease. Okay, so if I have a 20% decrease, how do I find my decay factor?
The 1 minus 0.2.
Perfect, which gives us 0.8. So now that I have a decay factor, I can write a model. So for my model, ending amount, how much do we start with?
120.
Good. 0.8 goes in our decay factor spot. Ooh, that's a good 8. And we raise it to the t power. So there's our model. And then, how much is left after 6 weeks? What do we do with that 6?
Plug it in for the t in
Plug
the
it
equation.
in for the t. Yep. So 120. Can you hear people talking in the background? Are they too loud?
Oh, no,
Okay.
You're fine.
Okay. My mom and sister are in the kitchen talking because we're leaving for vacation as soon as I'm done.
Oh, wonderful. Sounds like fun.
I'm so excited, yeah. Okay, sorry, what'd you get when you plug 6 in for t, what do you get?
I got 31.46.
Perfect.
And that's rounded up.
Yep. And it's
$31.46.
Perfect. Yep. So you can see how it's very similar to exponential growth. Now you're just taking away. It's getting smaller because it's, it's decreasing. All right, so let's do one without a table. And SUV depreciates 8% a year. If you buy a $26,000 SUV, what's the model and how much is it worth after 5 years?
So I would first need to figure out the growth factor for this.
Well, decay factor, yeah, because it depreciates.
Or decrease.
Yep. So as soon as you figure out it's decreasing, you say, okay, that means I have a decay factor. And I know that you're good. I know it's an exponential because it's percentage, right? And percent change is relative change, and that's exponential. So decay factor says 1 minus my 0.08. And what do we get?
Got 0.92.
0.92. So there's my decay factor. Okay, so what's the model going to look like?
See, and this is where I get stumped, is what I plug it into the...
Okay, so we'll always start with the variable, right? Your ending amount is what you're starting with.
Right.
Okay, so ending amount, we don't know, but that equals the beginning amount, which is how much?
26,000.
Yep. And then we put our decay factor in the middle, and we raise it to t. It might help. I don't know if it would help or not, but if you like to, when you're writing your notes, to put it in words, right? Amount at the end equals the beginning amount, and then inside here you could put plus. Why did I put plus there? Oh, it's a t. Oh my gosh. Beginning amount times the decay factor, and then up here is the time. Because sometimes you look at symbols and they don't mean anything. But if you write it out in words, you might be able to see how it all fits together.
I should probably start doing that.
Yeah. I did that. I took accounting this summer, and I did that a lot for the different things because they use a lot of different symbols and things that I don't know, shorthand. And so I had to write them out so I knew what the heck they were talking about. So, okay,
Right.
5 years.
Yeah, same way.
Yeah, and you got to do what works for you. So some people that might work for and some it might not. But okay, so what do we do with that 5 years?
Plug it in for the T.
Exactly. So ending amount is 26,000. Oops. Times 0.92 to the 5th year.
I got $17,136.12.
Perfect. Did you see I put that $ sign and then an equal sign? I don't know what's wrong with me today. Okay, yeah, perfect.
You're amped about going on vacation.
That's true. That is very true. And make sure that when you do this, right, it talks about depreciating. You know your value is getting less. So when you look after 5 years, make sure that number is less than what you started with. If you plugged in a wrong number somewhere, very easy, to make a mistake. Very easy.
Right.
Okay. I've got one more example that I want to do, and that's actually it for the entire section. And it's another table.
Okay.
That, again, I'm not going to make you do. Okay, so 25 minus 20 is 5. And when I take new minus old divided by old, I get 0.25. Then the next one, 30 minus 25 is 5. 5 divided by 25 is 0.20. Hopefully you've already noticed a difference. And 5 divided by 30 rounds to approximately 0.17. What do you notice about this particular table?
Absolute change stays consistent.
Yes, the absolute change. And absolute change is a number, right? Remember when we talked about yesterday, relative change is a percent, absolute change is a number. Absolute change refers to linear models, absolute change, whereas relative change is exponential, as we just experienced in our previous examples. So the fact that the absolute change stays the same, right? This right here, this is constant change. What have we talked about today that is described as constant change? Do you remember?
Oh, I'm sorry. I was writing this down.
Oh, you're fine.
Sorry, what was the question?
Constant change. The absolute change is the constant change because it's 5 each time. What did we talk about earlier today that was constant change? Section 25. Actually, I think I said reoccurring change, which is, same thing.
So we just talked about it, and I got to flip back to it.
It's okay. We talked about a whole lot of stuff in the last 50 minutes. Part of a linear model. Which part of the linear model is constant change? Happens over and over and over. Starts with an S.
Be the y or slope. I'm sorry.
Yeah, slope is the constant change in a linear model. So when you have when you have the absolute change that is the same, in this case it's a 5 each time, that's a constant change, happens the same over and over and over. That tells us not only do we have a linear model, but that tells us that our slope is 5. That describes our slope. So I can go ahead and write a linear model. Right, we talk about y equals, our slope comes first in front of x, plus our y-intercept, and the y-intercept is when x is 0. So up here, x is 0 when y is 20, so 20 is my y-intercept. So there's your linear model. And then the last piece, what is the amount after 8 weeks? Well, we got to plug the 8 in for x, right? So y equals 5 times 8 plus 20. And so that answer is 60. So you can also see how the answers that we're getting for the linear models are smaller because exponential just grows so much faster than linear. Yeah.
Okay.
So I like to do that one just because it kind of, we have that table, and from a table you can find a linear model or an exponential model depending what's the same. So in the earlier examples, all of our percent changes, that tells you exponential gives you, right, the percent increase or the percent decrease. The linear model gives you the slope. Yep.
Gotcha.
All right, so that's all I got. What questions do you have?
I don't know. Do you have another example for another relative change that stays the same? I know I just did it, but I kind of want to do it once more if that's possible.
Are you talking like one of these tables?
Yeah. Because I don't feel like I grasped a good hold of that like I did with the absolute change being the same.
Okay, well let's just look at this one. Even though we already did it. Now that we've talked about it, you might be able to see it a little bit easier. Does that make sense?
Mm-hmm.
Sometimes
I just feel like I didn't catch this one as good as I did the other one.
Okay, so I gotta find this. Okay. So the big thing to remember with these is that relative change is percent change. That's kind of the big key, and that's a takeaway from yesterday, from section 24. So when you look at this, right, absolute change, these are different, so we know it's not linear, because absolute change goes as linear. Since relative change is the same, we know that it's an exponential model. Okay, so percent change is 0.4. It's positive, and you can see that these numbers are getting bigger, so you know that you're going to have a growth factor. Right? Both of those things tell you it's a growth factor because, one, your relative change is positive, and two, your numbers are getting bigger. Right? So both things. So growth factor is 1 plus your percent change or percent increase, which is, in this case, the 0.4. So whatever is in this the relative change column, if you have an exponential model, you're either going to add that or subtract it from 1, depending if it's positive or negative.
Okay. Yep.
Right? Does that make sense?
Yeah. Yes.
Right. So that gives us a growth factor of 1.4, which that led us to. You'll notice that in our linear model, this very first value was our y-intercept. And in our exponential model, that very first value is our initial value. So you're going to use that first number when x is 0, you're going to use that both places. Whether it's exponential or linear, doesn't matter. It has two different spots, right? In linear, it's the y-intercept, because that's the starting point in a linear model. And the starting point in an exponential model is the initial value. So those are both starting points of where you're going to start.
Okay.
Does that help a little bit?
Yes.
Okay.
Yep.
And sometimes seeing them back to back helps a little bit. When I teach this in a face-to-face class, we do a linear and an exponential table back to back in the same day. Like almost the same numbers, just we change one thing to change it from absolute to relative. And I think that does help to see them back to back.
Yeah. Nope. That makes sense.
Okay. And I will be emailing, checking my email every day at least once. Tomorrow and Saturday may be a little tricky because we're driving, but I will be. I'll be checking when we stop. So,
Okay.
yeah. So if you have questions, feel free to shoot them to me, and I'll get back to you as soon as I can.
All right.
All right.
All right. Well, enjoy your vacation, Becky.
Thank you very much. Enjoy the last week of the summer. Well, of this class.
Oh, will do.
All right. I'll talk to you later.
Will do. All right. Take care. Thanks.
Yep.
Bye.
Bye.